We're going to take a very, very brief glimpse at brain stress circuits, and then we'll come back in later and kind of dissect this out into different pieces and different pathways. And I mean, do whatever you want, but I would suggest that instead of writing anything down about this, is just look at the PowerPoint slide or your diagram, follow along, and then we'll come back and address it in more detail later. Okay? So this is just an overview. Now, human beings can create their own internal anxiety for reasons we talked about, for worrying about things or regrets or what have you. But let's use the example of a person who's confronted with a real bona fide threat. Okay, somebody pulling a knife on them, chasing them down the street, something like that. Okay, so the threat in the environment, we're going to see that appraisal occurs on two basic levels. Okay, and it happens on the level of cortex. And again, we'll get to a lot of detail here in just a few minutes, and a more primitive level of threat appraisal occurring at the amygdala. And both of these brain structures independently evaluate potential danger in the environment, and their conclusions, we'll see, may match each other. They both are coming up with the same conclusion, but sometimes they don't. Sometimes the cortex arrives at a different conclusion than the amygdala. Okay, but in any event, what they do then is these two brain structures, let's say in this example that they agree. This is really and truly a life-threatening event happening right here. And so part of the brain stress circuits then are pathways that go from the cortex down into this brainstem nucleus called the locus coeruleus. And also, back here. There's separate pathways from the amygdala that feed also down into the locus coeruleus. And each one of them basically are saying danger. And some people have referred to the locus coeruleus as the adrenal gland of the brain. When it gets activated, then it explodes out a huge amount of release of norepinephrine throughout the brain. Almost all norepinephrine nerve cell bodies are down here in the brainstem, but they send out projections widely to different parts of the brain. And there's two things that happen when the locus coeruleus gets activated. One thing is that the human or animal in a split second goes to a state of hypervigilance. So if there's something dangerous, you got to be wide awake and really watching what's going on. The other thing is helps to facilitate the activation of some of these other elements of the brain stress circuits. So now we're going to go to the hypothalamus. And we're going to look at basically two things. One is, coming out of the hypothalamus is the sympathetic nervous system. And as it shows on the diagram, first off, it goes almost everywhere in the body. And when, let's say you almost have a car accident, but you just barely miss it, and racing heart, and sweaty hands and stuff like that, that immediate lightning fast response, and you have physiological responses, that's the sympathetic nervous system. These nerve cells are firing at a rate of 250 miles an hour. Okay, so they are almost instantaneous, and then you get that kind of response. Now, the sympathetic nervous system also sends axons down into the core of the adrenal gland. And the adrenal gland, about 10% of it is the central feature is called the adrenal medulla. And then about 90% of it on the outside is referred to as the adrenal cortex, okay? And each one of those make different stress hormones. So in an instant, it's activating the adrenal medulla, which dumps two important stress hormones into circulation, okay? And you can see here on the diagram, adrenaline and norepinephrine. So these get dumped into circulation, and what that means is for these hormones to reach their target, wherever it is in the body, okay, it's going to take 10, 15 seconds or so, because you're relying on circulation to deliver it there. So the sympathetic nervous system is a nerve impulse, but here this hormonal response will take a little while to kick in. Okay, so that is the sympathetic nervous system. Now we're going to look at two what are referred to as neuroendocrine pathways, and they're very, very important. The first one is the hypothalamus, pituitary, and the adrenal cortex. So this is the often referred to as the HPA axis, hypothalamus pituitary adrenal cortex. And at the level of the adrenal cortex, remember the outer part of the adrenal gland, then it releases into circulation a group of hormones. If you've been reading Sapolsky's book, you really know about this already. Glucocorticoids, but the one that's one of those that's the most important in human beings is cortisol, and that gets dumped into circulation, also requiring time to get to other parts of the body. And then we have the hypothalamic pituitary thyroid axis, and we're going to take a close look at that also. Under normal conditions, the hypothalamus is regulating, it's watching and monitoring thyroid hormone levels. And if there's a change in that, it will get activated to produce more thyroid hormones. In a fight or flight situation, it also increases the release of the two thyroid hormones, T3 and T4. And thyroid, primarily, the impact of thyroid is it has an effect on almost every cell in the body. It regulates the degree of overall metabolism. So people who say, eat a certain amount of food and they gain weight, they can't burn calories as much, and that could be one reason that they're gaining weight. Other people who can eat a lot and they never gain any weight, there are different reasons for that, but oftentimes with thyroid, if you have hypothyroid, then people are more sluggish, they put on weight, and then don't burn calories. On the other hand, somebody has hyperthyroid, it's going to be just the opposite. So what happens really in a fight or flight response is extra thyroid hormone will activate or amplify what you get from the sympathetic nervous system. So it kind of works hand in hand. And that's it, okay? Now there are details, but these are the primary parts of the brain that get activated, and the primary ways it delivers that activation out into the body.